In the waning days of December 1941, an air of profound disbelief settled over the foreman at Ford's River Rouge facility in Dearborn, Michigan. His gaze was fixed not upon the familiar schematics for a robust V8 engine block, but rather on intricate engineering blueprints detailing a formidable 30-ton armored behemoth bristling with a 75 mm cannon. The devastating attack on Pearl Harbor had occurred merely days prior, and the United States government had communicated an unyielding directive. The very assembly lines that had, until recently, busily produced civilian sedans and elegant coupes were now mandated to commence tank manufacturing with immediate urgency. This represented an unprecedented and seismic shift in industrial priorities. This monumental transformation was anything but gradual. It was an abrupt and absolute reorientation. The Automotive Council for War Production, an influential body established in early 1942, issued a categorical decree to Detroit's industrial titans, Ford, Chrysler, and General Motors, that the fabrication of all civilian vehicles would cease entirely by February 1942. This left an astonishingly tight 2-month time frame for these colossal enterprises to completely retool their extensive factory infrastructure, an undertaking valued at hundreds of millions of dollars, signifying a conversion of unparalleled scale and speed. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Even before America's formal entry into the global conflict, Chrysler's foresight was evident as its tank arsenal in Warren, Michigan, commenced construction in September 1940. Spanning an expansive 113 acres of what was formerly agricultural land, this facility rapidly took shape. By January 1942, a mere handful of months later, the initial M3 Grant medium tanks were triumphantly emerging from the very production lines where Dodge trucks had been meticulously assembled in the preceding months, a testament to the nation's burgeoning industrial might. The rationale underpinning this dramatic shift from automotive production to armaments was remarkably clear and compelling. Automobile manufacturers inherently possessed 3 indispensable elements crucial for the prodigious output of tanks. Firstly, they commanded immense physical assets, sprawling edifices equipped with powerful overhead cranes, sophisticated electrical systems capable of powering countless machines concurrently, and dedicated railway spurs facilitating seamless transportation. Secondly, their expertise in high-volume manufacturing surpassed that of any traditional armaments producer. While venerable European firms like Germany's Krupp crafted exceptional tanks, their methods were akin to meticulous artisans. Detroit, conversely, engineered products with the continuous, relentless, and standardized flow of a powerful river. Thirdly, their highly skilled labor force already possessed an intimate understanding of working with steel, adeptly operating stamping presses, and precisely integrating thousands of complex components into a fully functional mechanical marvel. Yet, what truly distinguished this transition as revolutionary was not merely the repurposing of car plants for tank production, but their profound optimization for this new purpose in ways conventional arsenals could never achieve. The Fisher Body Division of General Motors, renowned for shaping automobile bodies, was transformed into the primary manufacturer of the M4 Sherman's formidable hull sections. Here, 5-inch thick armor plate was handled with the same industrial efficiency and precision that had previously been applied to the sheet metal for Buick hoods fed into colossal hydraulic presses as raw material. Chrysler engineer Bob Gregory later recounted that the paramount challenge was not the inherent technical complexity of tank components, but rather instilling in the workforce the understanding that a weld on a transmission housing demanded the identical, unwavering precision as a critical weld on a tank's final drive system. The sheer velocity of this industrial metamorphosis continues to defy belief. Chrysler's tank arsenal delivered its inaugural M3 Lee medium tank in April 1941, an astonishing feat achieved just 7 months after the groundbreaking ceremony. Ford's historic Highland Park plant, the revered birthplace of the Model T, was already fabricating tank engines by March 1942. The entire sprawling supply chain underwent a complete reorganization within a matter of months. Steel mills rapidly recalibrated their rolling schedules to produce thicker armor plate. Rubber manufacturers diverted their substantial output towards track components, and electrical goods producers pivoted their focus from car radios to the specialized motors essential for powering tank turrets. The linchpin of this industrial feasibility was an unwavering commitment to standardization. The iconic Sherman tank was conceived from its very inception with the explicit intention of being manufactured within existing automotive plants. Its visionary designers at the Aberdeen Proving Ground engaged in direct consultations with automotive engineers in 1941. Posing a question that no military procurement officer had ever seriously contemplated. How can we engineer a tank that can be constructed using established car manufacturing methodologies? The innovative solutions included features such as bolted rather than welded turrets in early models, ensuring interchangeable parts across different variants, and incorporating engines that mechanics already proficient in servicing trucks could readily maintain. Franklin Roosevelt, with profound prescience, grasped a fundamental truth in 1940 that would ultimately define the entire global conflict. Factories win wars, just as surely as soldiers do. On December 29, 1940, a full 11 months before the attack on Pearl Harbor, he addressed an audience of 60 million radio listeners in his seminal Arsenal of Democracy fireside chat. This powerful phrase was far more than mere rhetoric. It served as a precise blueprint for transmogrifying America's vast industrial capacity into a weapon more devastating than any bomber or battleship. Roosevelt articulated production targets that initially seemed utterly preposterous: 50,000 aircraft annually, a staggering figure given that the entire U.S. aviation industry had produced only 6,000 planes in 1939. He demanded tanks, ships, and artillery in quantities so immense they would unequivocally bury the Axis powers under an overwhelming weight of material superiority. The principal administrative instrument Roosevelt employed was the War Production Board, WPB, formally established in January 1942 under the astute leadership of Donald Nelson, a former Sears executive with an exceptional understanding of complex supply chains and logistics. Nelson's WPB wielded authoritarian powers that would have been utterly inconceivable in peacetime America. This powerful board could issue directives to any factory ordering an immediate halt to civilian goods production. They possessed the authority to meticulously allocate vital raw materials, steel, aluminum, rubber, copper, precisely dictating which industries receive specific tonnages. Furthermore, they could prioritize contracts, meaning that an order for tanks would leapfrog ahead of virtually every other item in the national production queue. However, a crucial aspect, often overlooked in historical documentaries, is that the government did not merely commandeer these factories through rousing patriotic speeches. Instead, they strategically deployed cold, hard financial incentives that rendered war production irresistibly profitable for manufacturers. The cost-plus contracting system guaranteed companies reimbursement for all their production costs, plus a predetermined profit margin, typically ranging from 7% to 10%. This ingenious system effectively eliminated all financial risk for participating corporations. For instance, if Chrysler invested $100 million in constructing and operating a tank plant, the government fully reimbursed every single penny of that expenditure and then added a substantial profit of $7 to $10 million. The traditional practice of competitive bidding vanished entirely. The government's overriding imperative was production speed, not cost savings. The Defense Plant Corporation, DPC, a powerful subsidiary of the Reconstruction Finance Corporation, financed an astonishing $9 billion worth of new factory construction between 1940 and 1945. Their role extended beyond simply loaning money. They actively constructed entire industrial facilities and then leased them to manufacturers for merely nominal fees. The Chrysler Tank Arsenal, for example, was fully government-funded, government-owned, and expertly operated by Chrysler. Following the cessation of hostilities, companies were given the lucrative option to purchase these state-of-the-art plants at heavily discounted bargain prices. This represented corporate welfare on an unprecedented scale, making companies quite literally salivate at the prospects. General Motors alone secured over $10 billion in war contracts between 1940 and 1945, an amount roughly equivalent to a staggering $180 billion in today's economic landscape. The sophisticated intellectual framework underpinning this massive industrial mobilization was derived from the insights of economists who had meticulously analyzed the production failures of World War I. During 1917 and 1918, the United States had stumbled into the conflict with a glaring absence of industrial coordination, leading to widespread shortages, crippling bottlenecks, and scandalous profiteering. Bernard Baruch, who had effectively managed President Wilson's War Industries Board, advised Roosevelt to diligently avoid these prior errors by establishing centralized control from the very outset. The WPB therefore adopted a proactive stance, not waiting for shortages to manifest, but instead forecasting needs 2 years in advance and meticulously allocating resources accordingly. Labor, too, was mobilized with an equivalent degree of precision and strategic foresight. The War Manpower Commission, established in April 1942, possessed the authority to direct workers into industries deemed essential for the war effort. Unemployment, which had stood at a significant 14.6% in 1940, virtually disappeared by 1943. Factories that had languished on single shifts throughout the Depression era of the 1930s now operated tirelessly on 3 shifts around the clock. The government generously subsidized extensive training programs, intensive, rapid 8-week courses that imparted vital skills such as welding, machining, and assembly to individuals who, in many cases, had never before set foot inside a factory. Roosevelt's profound genius lay in his acute recognition that American industry's peacetime overcapacity, all those dormant factories and underutilized resources from the Great Depression, could be strategically converted into a formidable wartime overcapacity, relentlessly focused on vanquishing the enemy. Every single Sherman tank that rolled off a repurposed automobile plant assembly line represented an embodiment of industrial muscle that Germany and Japan simply could not hope to match. Their respective industrial complexes were already operating at maximum capacity by 1939, whereas America's were nowhere near their full potential. The Willow Run project was widely considered an impossibility. When Charles Sorensen, Henry, Ford's trusted chief lieutenant, declared in early 1941 that Ford would construct a factory capable of producing one B-24 Liberator bomber every hour, aviation experts across the nation openly scoffed. Established aerospace giants like Boeing and consolidated aircraft manufactured bombers in small, meticulously crafted batches using highly skilled artisans. Sorensen, however, envisioned building them with the same mass production efficiency as Model T automobiles. The monumental facility that ultimately materialized in Ypsilanti Township, Michigan, subsequently became the definitive blueprint for how America would manufacture everything from heavy bombers to vital tanks, though it nearly buckled under the sheer weight of its own audacious ambition during its initial phases. Construction commenced in April 1941 on what would become the singular largest manufacturing space ever contained under one roof, an immense 5 million square feet, ingeniously shaped like an L that stretched over a mile in length and a quarter-mile in width. The sheer scale of the building alone necessitated an astounding 440,000 cubic yards of concrete and 29,000 tons of structural steel. Ford engineers meticulously designed a groundbreaking production line where a B-24, entering as a collection of 450,000 discrete components at one end, would emerge as a fully functional bomber at the other. This assembly line advanced at an astonishingly precise pace. Every 63 minutes, one complete aircraft was delivered. Crucially, what rendered Willow Run profoundly relevant to Sherman tank production was the direct applicability of its underlying principles. The exact same manufacturing philosophies, albeit scaled differently, were successfully transferred to tank production. While Ford did not produce Shermans at Willow Run itself, the engineering wisdom perfected there permeated throughout the entire automotive tank manufacturing sector. This philosophy advocated for breaking down complex weapon systems into manageable subassemblies, constructing each subassembly on dedicated, specialized lines, and then bringing them together at the final assembly stage with mathematical exactitude. The M4A3 Sherman variant, notably powered by Ford's GAA V8 tank engine, perfectly encapsulated this innovative production thinking. The initial phases of the ambitious manufacturing endeavor presented significant obstacles, almost validating the predictions of those who harbored doubts. When the Willow Run facility commenced operations in September 1942, its output for that entire month amounted to a mere single B-24 bomber. Workers frequently struggled to locate the necessary tools, and components often arrived out of sequence, disrupting the flow of production. The assembly line experienced continuous stoppages, as parts consistently failed to fit together accurately. By December of that same year, the plant had managed to construct only 56 bombers, a figure dramatically short of the envisioned 1 per hour production rate. Frustration among the workforce led to an alarming labor turnover rate of 50% as countless employees resigned. The severe scarcity of adequate housing compelled many workers to sleep in their vehicles or reside in cramped apartments, sometimes with as many as 10 individuals sharing a single unit. The transformative solution implemented by Sorensen was deeply rooted in established automotive manufacturing principles, an unwavering commitment to standardization, and the pervasive use of specialized jigs. This approach mandated that every single component had to align perfectly each and every time it was utilized, necessitating incredibly fine manufacturing tolerances, often measured in mere thousandths of an inch. Ford meticulously fabricated 7,500 distinct jigs, custom-designed fixtures engineered to hold parts in precise, unvarying positions during critical processes such as welding or riveting. A wing section, which previously demanded hours of intricate labor from highly skilled craftsmen, could now be assembled by relatively semi-skilled personnel in a matter of minutes, thanks to these jigs that absolutely guaranteed correct positioning. This innovative methodology represented the pivotal advantage. Traditional aircraft manufacturers typically depended on the individual skill and judgment of their workers to compensate for inherent variations in parts. Ford, through its systematic implementation of jigs, fundamentally eliminated such variations entirely. This identical jig philosophy was subsequently applied with remarkable success, utterly transforming the production of the Sherman tank. At Chrysler's tank arsenal, the construction of a single hull necessitated approximately 5,000 individual welds. Early production efforts were plagued by significant quality control issues, including welds that frequently cracked, armor plates that were misaligned, and hatches that failed to seal properly, compromising the integrity of the vehicle. However, by mid-1942, engineers had successfully developed and deployed sophisticated positioning jigs for every critical weld point on the tank. This ingenious system enabled workers with as little as 8 weeks of specialized training to produce welds that consistently met stringent military specifications, simply because the jig held every element in a perfectly square and stable configuration. Consequently, the tank's assembly evolved from what might be described as an intricate metalwork art project into a meticulously choreographed series of precise, repeatable steps. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment below about where you are from and what you think about the video topic. By 1944, the Willow Run facility finally realized its ambitious promise, consistently achieving a production rate of 1 bomber per hour, and on occasion even surpassing this impressive target. Between 1942 and 1945, the plant ultimately produced an astonishing 8,685 B-24s, a figure that accounted for nearly half of all Liberators ever constructed. The profound insights gleaned from this experience were subsequently disseminated and adopted across virtually every war production facility, underscoring a crucial lesson that even the most daunting complexity could be effectively overcome through meticulous process engineering, rigorous standardization, and a pragmatic acceptance of the iterative nature of manufacturing. Understanding that one might produce 100 adequate examples before finally perfecting the 101st. In stark contrast, German factories seemingly failed to internalize this pivotal lesson. Their persistent approach involved attempting to construct each individual tank to an absolute standard of perfection on the very first attempt. The Sherman tank, however, was deliberately conceived and engineered to be merely good enough, a design philosophy that reportedly drove German tank commanders to utter exasperation. When the Panzertruppen first encountered the American Shermans in North Africa during late 1942, they observed a profoundly peculiar characteristic. These American tanks evidently were not designed to surpass or out-armor German panzers in individual combat. Instead, their overarching objective appeared to be simply to out-exist them through sheer numerical superiority. The overarching design philosophy behind the M4 Sherman revolved around a question that might strike one as almost cynical in its pragmatism. What is the absolute minimum capable tank we can manufacture in overwhelmingly vast quantities? The choice of engine, in particular, illuminates this strategic imperative. The original M4 utilized a Continental R975 radial aircraft engine, essentially a power plant designed for an airplane adapted and bolted directly into a tank. The rationale was simple, yet brilliant. America already possessed the industrial capacity to mass-produce radial engines for its burgeoning aircraft fleet, and the entire supply chain for such components was already robustly established. Later variants of the Sherman incorporated other readily available power plants, such as the Chrysler A57 multibank, which was quite literally comprised of 5 automobile engines linked to a single drive shaft, or Ford's GAA V8, a heavily modified bomber engine. This approach stood in stark contrast to German tank development. The formidable Panther, for instance, was powered by the Maybach HL230, a highly specialized purpose-built tank engine that demanded bespoke manufacturing processes. Consequently, when a Maybach engine failed, it necessitated highly specialized Maybach-specific replacement parts. Conversely, if a Sherman's engine malfunctioned, crews could often cannibalize parts from readily available trucks or even other damaged Sherman tanks, significantly easing maintenance and logistics. The Sherman's primary armament, the 75mm M3 gun, was likewise a deliberate selection based on adequacy rather than outright superiority. American ordnance officers, as early as 1941, were well aware that the 75mm round would struggle to penetrate the heavy frontal armor of German tanks. However, this was not the gun as sole or even primary purpose. The weapon was highly effective at firing high-explosive shells against infantry formations, capable of destroying medium tanks at reasonable engagement ranges, and, most critically, its ammunition was fully interchangeable with other American military systems. This standardization of ammunition dramatically simplified logistical operations. A single supply truck could transport one type of 75mm shell that was compatible with Sherman's, M3 half-tracks, and various towed anti-tank guns, streamlining the entire supply chain. The thickness of the Sherman's armor tells a similarly pragmatic story. Its front hull measured 51mm thick, sloped at a 56-degree angle, providing an effective thickness of approximately 90mm against incoming projectiles. In comparison, German Panthers featured 80mm frontal armor, sloped at a comparable 55 degrees, yielding an effective thickness of around 140mm. On paper, the Sherman appeared to be significantly outmatched in terms of defensive capability. However, this disparity highlights a crucial engineering trade-off. Thicker armor inherently demands a heavier suspension system, more powerful engines to propel the increased mass, wider tracks to distribute the weight, and stronger transmissions to handle the additional strain. The Panther, for instance, weighed a substantial 45 tons, whereas the Sherman tipped the scales at a comparatively lighter 33 tons. This 12-ton difference was strategically significant, meaning Shermans possessed the agility to cross numerous bridges that Panthers simply could not traverse. They could be transported on standard Allied flatbed rail cars without issue, consumed considerably less fuel, and were significantly easier to recover when disabled or damaged in the field. The Sherman's transmission system achieved a legendary status, albeit for distinct reasons. It employed a synchromesh gearbox, a design very similar to those found in civilian trucks. This allowed drivers to shift gears smoothly without the complex requirement of double clutching, thereby reducing both the necessary training time for crews and the mechanical stress placed upon the gearbox itself. In stark contrast, the Panther's transmission was notoriously fragile and demanded a delicate touch, requiring double clutching and a degree of mechanical sympathy that was often lacking among the poorly trained, late-war German crews. American tank crews, after just a few weeks of concentrated training, could competently operate a Sherman. A Panther, by comparison, demanded months of dedicated experience and careful handling. Maintenance accessibility was a paramount design consideration, integrated into every panel and hatch of the Sherman. A trained crew, utilizing standard tools, could remove the Sherman's engine in approximately 2 hours. The entire transmission unit could be extracted for repair in a field workshop within a single day. German tanks, particularly the formidable Tigers and Panthers, frequently required the partial disassembly of numerous surrounding components merely to access a problematic area. A thrown track on a Sherman might take a single crew around 30 minutes to repair, allowing the tank to quickly return to action. A thrown track on a Tiger, however, could immobilize the massive vehicle for hours and often necessitated the assistance of specialized recovery vehicles. This was not indicative of American engineering incompetence, rather, it represented American engineering genius applied specifically to the demands of industrial warfare. The designers at Aberdeen Proving Ground posed a critical question: what ultimately wins battles, 10 superior tanks or 50 adequate ones? Their decisive answer was 50, and they proceeded to design a tank that automobile factories could realistically construct at that unprecedented scale. While the Germans engineered individual masterpieces, America designed highly effective mass-produced widgets. The sheer scale of the production figures is almost staggering. Between February 1942 and July 1945, American factories collectively produced an astounding 49,234 Sherman tanks across all its various configurations. To truly grasp this magnitude, consider that this represents 4,934 complete tanks manufactured in roughly 3.5 years. This translates to an average production rate of approximately 1,170 Shermans per month, or roughly 39 units every single day, without interruption, for the duration of the war. Now juxtapose these figures with Germany's output of its two most renowned heavy tanks, approximately 6,000 Panthers between January 1943 and April 1945, and a combined total of roughly 350 Tiger IV and Tiger II models produced throughout the entire war. Germany's total production of all tank types from 1939 to 1945 amounted to approximately 67,000 vehicles. America, through its production of Shermans alone, manufactured more tanks than Germany produced Tigers and Panthers combined, by a factor of 8. An examination of peak production months vividly illustrates the profound disparity. In December 1943, American factories completed an astonishing 2,200 Sherman tanks. This equates to one Sherman rolling off a production line somewhere in America every 17 minutes around the clock for the entire month. The Chrysler Tank Arsenal in Warren, Michigan, by itself, produced 18,113 tanks between 1940 and 1945. a figure that surpasses Germany's entire Panther production. The Fischer tank division of General Motors contributed an additional 11,352 M4A2 variants. Ford's extensive facilities added thousands more of the M4A3 model, which utilized the GAA engine. Even the Lima Locomotive Works in Ohio, traditionally a manufacturer of trains, successfully built 1,685 Shermans, demonstrating the pervasive integration of war production. German production, conversely, peaked at significantly lower numbers and commenced much later in the conflict. The Panther tank, for instance, did not enter production until January 1943, by which point American industry had already manufactured well over 10,000 Shermans. Germany's most productive month for Panther manufacturing occurred in July 1944, when they completed approximately 380 units. In sharp contrast, American plants during that very same month produced over 1,600 Shermans. The Tiger Wine's peak production month was April 1944, with an output of only 104 units. America, with its immense industrial capacity, was capable of building more tanks in a single week than Germany produced Tigers in its most successful month. Why did such a staggering disparity in production capability exist? The answer begins with a fundamental difference in raw industrial capacity. In 1943, the United States produced an immense 85 million tons of steel, while Germany's output stood at 34 million tons. This represented a substantial 2.5 to 1 advantage for America in the most fundamental ingredient required for tank construction. American aluminum production in 1943 reached 920,000 tons, compared to Germany's 250,000 tons, marking a nearly 4 to 1 advantage in a critical material necessary for engines and aircraft. This profound resource gap was, quite simply, unbridgeable. Factory construction timelines further illuminate another crucial dimension of this disparity. When America identified a need for increased tank production, it simply proceeded to build more factories. The Grand Blanc tank arsenal in Michigan, operated by Fisher Body, broke ground in January 1942 and delivered its very first tank by August 1942, an astonishing turnaround of just 7 months from initial groundbreaking to operational deployment. This massive facility spanned 5 million square feet and involved an investment of $37 million entirely funded by the government. Germany, however, found itself unable to construct new tank plants in 1943 because relentless Allied bombing campaigns systematically targeted any significant construction projects, forcing them to disperse their existing production into smaller, inherently less efficient facilities, further hindering their war effort. The aspirations of Germany to match the formidable industrial output of the Allies were systematically undermined by a critical shortage of skilled labor and less efficient manufacturing infrastructure. By 1943, American tank factories, veritable behemoths of production, engaged the efforts of over 100,000 individuals, a significant proportion of whom were women courageously venturing into the realm of heavy industry for the very first time. In stark contrast, Germany grappled with a persistent scarcity of experienced workers, increasingly resorting to the coerced labor of forced laborers and concentration camp internees, whose output was predictably characterized by dismal productivity and flagrant quality control failures. A Sherman tank, meticulously crafted by a properly trained American artisan in the bustling factories of Detroit, exhibited unwavering consistency in its quality and performance. Conversely, a Panther tank, cobbled together by a famished French prisoner in the grim year of 1944, often emerged with critical, potentially fatal, structural or mechanical deficiencies. The cold, hard calculations of strategic warfare were unyieldingly harsh. Even if German armor could achieve a formidable 3-to-1 kill ratio against the M4 Shermans, a feat rarely accomplished in the crucible of actual combat engagements, the United States possessed the immense industrial capacity to absorb the loss of 3 Shermans for every Panther vanquished, all while maintaining a decisive numerical advantage on the battlefield. Germany, however, could ill afford any significant losses whatsoever. By the middle of 1944, American manufacturing facilities were churning out replacement Sherman tanks at a pace that far outstripped the rate at which German forces could destroy them. The conflict had thus devolved into an intractable mathematical problem that Germany found itself utterly incapable of resolving. We invite you to stay with us and watch the end of this insightful video. Your support in the form of a like and a subscription would be profoundly appreciated. Please also consider leaving a comment below, sharing where you are from, and your thoughts on the compelling topic discussed in this presentation. The innovative assembly line methodologies that underpinned the rapid construction of Sherman tanks were essentially the fundamental principles of Henry Ford's Model T production, but amplified to an unprecedented degree and fortified with robust, welded armor. Stepping into the vast expanse of the Chrysler tank arsenal in Warren during the pivotal year of 1943 was akin to witnessing a meticulously choreographed industrial ballet, a spectacle far removed from the more traditional, slower pace of conventional weapons manufacturing. The initial stage involved the hull, which began its journey as colossal flat steel plates, each 5 inches thick, arriving from specialized steel mills already precisely cut to exact specifications. These formidable plates were then guided into immense stamping presses, capable of exerting an astonishing 2,000 tons of pressure, bending solid steel with the apparent ease of mere sheet metal. The role of the press operator was not one of intricate craftsmanship or bespoke artistry. Rather, it demanded unwavering vigilance in monitoring gauges and executing precise lever movements at predetermined intervals. The revolutionary concept of subassembly reigned supreme. Instead of constructing a tank sequentially from front to back within a single static location, the Sherman was brought to life through a parallel manufacturing process, unfolding simultaneously across numerous specialized production lines. One dedicated team meticulously assembled the intricate transmission system. Another group expertly fabricated the complex turret basket. A third unit was responsible for constructing the rugged suspension bogies. And yet a fourth team focused on assembling the sophisticated engine compartment. Each of these distinct subassemblies embarked on a journey, propelled by overhead conveyors or gliding effortlessly on rolling platforms, until they converged seamlessly onto the main assembly line. This ingenious system eliminated the inefficiencies of sequential waiting, ensuring that no single group was idle, anticipating the completion of another's task. Instead, every segment of the workforce operated in perfect synchronicity, advancing different tanks through various stages of completion simultaneously. The welding operation, in particular, showcased how automotive industry paradigms truly revolutionized the production of armored vehicles. A single Sherman hull necessitated approximately 5,000 individual welds to securely join all its formidable armor plates. Traditional welding practices, common in shipyards or conventional arsenals, relied upon highly skilled welders proficient in executing any type of joint at any conceivable angle. Chrysler, however, ingeniously categorized these 5,000 welds into distinct types: flat welds, corner welds, overhead welds, and so forth. Workers were then rigorously trained to specialize in just one specific category. A specialist in flat welds, for instance, might execute the identical weld 200 times within a single shift, thereby achieving an unparalleled level of speed and consistency that a generalist welder, burdened by diverse tasks, could simply not replicate. The strategic deployment of jigs and fixtures served to entirely eliminate any element of guesswork from the assembly process. The foundational structure of the lower hull was securely cradled within a massive steel fixture, which held the floor plate, side plates, and sponsons in absolute, unwavering alignment while the welders performed their tasks. These fixtures boasted an extraordinary degree of precision, accurate to within an astonishing 1/32 of an inch. Workers were not required to painstakingly measure angles or verify alignment. The sophisticated jig inherently performed these critical functions automatically. This groundbreaking methodology enabled Chrysler to recruit and train welders in a mere 6 to 8 weeks, a stark contrast to the traditional multi-year apprenticeships that German manufacturing firms typically demanded. By 1943, the average tank welder at Chrysler had been removed from their civilian occupation for a mere 90 days, a testament to the efficiency of the training. The intricate process of turret assembly unfolded on specialized rotating pedestals, which afforded complete and unimpeded access to all sides of the component without the need for manual repositioning. Workers meticulously installed the gun mantlet, precisely mounted the potent 75mm cannon, fitted the essential recoil mechanism, installed the gunner's periscope, and connected the traverse motors, all while the turret rotated at a controlled, slow pace on its powered stands. This station-based approach ensured that each worker remained in a fixed location, with all necessary tools and components immediately within reach. There was no time wasted traversing back and forth to tool cribs, no frantic searching for elusive parts. Rather, every required item flowed directly to the worker's station. The final assembly phase represented the ultimate convergence point of all preceding efforts. The fully completed hull arrived on designated rails, while powerful overhead cranes meticulously lowered the engine and transmission, pre-mated as a single cohesive unit. 4 skilled workers expertly guided this formidable power pack into its precise position, while others simultaneously installed the critical drive shaft. The entire installation of the power pack was completed in approximately 45 minutes. A remarkable feat when compared to German tank plants, where engine installation frequently consumed an entire day, often requiring painstaking custom fitting and intricate adjustments. Immediately following, the fully equipped turret was delicately lowered onto the hull ring, arriving complete with its main gun, ammunition racks, communication radios, and crew stations. The entirety of this final assembly process, from a bare hull to a fully operational running tank, typically required only about 8 hours. Crucially, quality control was embedded at each individual station, rather than being relegated to a single final inspection point. Inspectors, armed with precise go-no-go gauges, continuously scrutinized welds. Should a weld fail inspection, the worker responsible immediately rectified the defect, preventing it from progressing to subsequent stations. This proactive approach caught defects early when they were significantly less costly and time-consuming to address. By the time a Sherman tank reached the test track for its final trials, it had undergone dozens of rigorous inspections. The German methodology, in stark contrast, involved inspecting completed tanks, which often necessitated their partial or full disassembly to correct identified problems. A catastrophically inefficient system. The dedicated individuals who ultimately constructed the astounding 49,000 Sherman tanks were not the typical workforce anticipated for such heavy industrial endeavors. In 1940, American factories were predominantly staffed by white men, many of whom were immigrants or the descendants of immigrants, possessing industrial experience often inherited through generations. By 1943, however, the demographic landscape of tank plants had undergone a radical transformation. Women constituted a remarkable 40% of the labor force at Chrysler's tank arsenal. African Americans occupied positions previously exclusively reserved for white workers, and even elderly individuals who had retired years prior returned to the production lines, driven by patriotism and necessity. This profound demographic shift on American factory floors proved to be as revolutionary as the sheer volume of production itself. The iconic image of Rosie the Riveter was not mere propaganda, she represented a compelling statistical reality. Women entered the demanding realm of heavy manufacturing in unprecedented numbers, primarily because a vast proportion of men had departed for military service. Between 1941 and 1945, the military conscripted an astonishing 16 million Americans, thereby creating severe labor shortages that would have undoubtedly crippled industrial production. Were it not for one crucial factor, women stepped in to fill these critical gaps. At the Fisher Tank Arsenal in Grand Blanc, Michigan, women skillfully operated 20-ton overhead cranes, managed powerful stamping presses, and performed intricate welding on thick armor plate. These were by no means light assembly tasks. They were physically arduous positions that demanded considerable lifting, climbing, and the proficient handling of potentially dangerous equipment. The training programs designed for this new workforce were remarkable for their exceptional efficiency and striking brevity. The War Manpower Commission took the initiative to establish comprehensive engineering, science, and management war training programs at universities and vocational schools across the nation. A typical welding course, for instance, spanned just 6 weeks, with students attending 6 days a week for 8 hours each day. Participants diligently practiced on scrap steel until they could consistently produce flawless welds, after which they graduated directly to the factory floors. Training for machine operation followed a similar intensive model, typically lasting 4 to 8 weeks of focused instruction on lathes, milling machines, or drill presses. The long-held notion that skilled manufacturing required years of arduous apprenticeship simply evaporated under the pressing exigencies of wartime necessity. Production shifts operated around the clock, structured into 3 continuous 8-hour rotations. The first shift commenced at 7 hours a.m., the second at 3 hours p.m. Time Chicago's, and the third, the graveyard shift, began at 11 p.m. This rigorous schedule ensured that tank plants never ceased operations, never went dark. As one crew completed its shift and departed, another arrived within minutes, seamlessly picking up precisely where the preceding shift had left off. Workers on the third shift, known as the graveyard shift, received a 10% differential pay. Yet recruitment for the midnight to 8:30 a.m. work remained persistently challenging. Factories proactively established cafeterias that operated 24 hours a day, acknowledging that fatigued and hungry workers were prone to errors that could potentially ruin a tank hull valued at thousands of dollars. The rapid influx of workers almost immediately precipitated a severe housing crisis. Chrysler's tank arsenal, at its peak production, employed an astounding 25,000 individuals. But Warren, Michigan, was simply not a municipality equipped to accommodate such an explosive population surge. The Federal Public Housing Authority responded by constructing emergency housing projects comprising basic apartments and dormitories, which were erected in a matter of months. The Willow Run Housing Project, situated near Ford's massive bomber plant, gained notoriety for its 3,000 trailers and temporary housing units, densely packed into often muddy fields. Workers frequently shared bedrooms on opposite shifts. One would sleep while the other worked, a practice colloquially termed hot bunking, a term borrowed directly from the U.S. Navy. Wages, while considered good by the prevailing standards of the Great Depression, were by no means extravagant. A tank welder in 1943 earned approximately 90 cents per hour, amounting to about $37 for a standard 40-hour week, with additional pay for overtime. This equates to roughly $650 per week in 2025, representing a solid middle-class income. However, women often received less remuneration than men for performing identical work, typically earning 60–70% of male wages, though even this represented a degree of progress from pre-war disparities. African American workers faced similar wage discrimination and were frequently assigned the most arduous, dirtiest, and most dangerous jobs, such as foundry work, sandblasting, and heavy lifting. Workplace injuries were regrettably common and often severe in nature. The very act of metalworking is inherently perilous, involving moving machinery, massive components, searing hot welding slag, and overhead cranes maneuvering multi-ton loads. The Bureau of Labor Statistics meticulously recorded over 37,000 workplace fatalities in American factories between 1942 and 1945. Tank plants, specifically, reported injury rates that were higher than the national average, primarily due to the immense weight and sheer size of the components being handled. A dropped armor plate, for instance, could instantaneously crush a worker. Welding in the cramped, confined spaces within tank hulls frequently led to severe burns and exposure to toxic fumes. Despite these inherent dangers, worker turnover at tank plants was surprisingly low once individuals had successfully navigated the initial 3 months of employment. The powerful combination of a profound patriotic purpose, consistent and steady pay, and a strong sense of community among the workers fostered remarkable retention. These individuals understood that their labor profoundly mattered. Every Sherman tank that rolled off the assembly line represented a tangible hope that sons, brothers, and husbands might ultimately return home alive. Germany's ultimate defeat in World War II was, in essence, forged within the vast industrial complexes of Detroit, Warren, and Grand Blanc long before any Sherman tank engaged an enemy in combat. This assertion is not a mere exaggeration. It is a demonstrable truth rooted in the cold precision of mathematics. By the pivotal year of 1944, the German Wehrmacht found itself confronting an utterly insurmountable challenge. While their armored vehicles, such as the formidable Panther and Tiger tanks, often boasted individual combat superiority, their crews frequently possessed greater battlefield experience, and their tactical doctrines had been meticulously honed over years of intense conflict. These advantages proved ultimately inconsequential. They were simply being engulfed by an unrelenting deluge of American steel, which arrived at the front lines with a speed and volume that far outstripped their capacity for destruction. The relentless pace of material attrition, therefore, narrates the tale of the war's outcome with brutal and uncompromising clarity. A compelling illustration of this industrial disparity emerged during Operation Cobra, the critical American breakout from Normandy, in late July 1944. The initial spearhead of this offensive comprised approximately 1,500 Sherman tanks. In the first tumultuous week of engagements, German forces managed to neutralize around 300 of these American machines. A 20% loss rate might at first glance appear catastrophic and profoundly damaging. However, this perception quickly dissolves when one considers the immediate response. American supply depots in England promptly dispatched 450 replacement Shermans across the Channel to France. Consequently, the U.S. Third Army, under the dynamic leadership of General Patton, did not merely maintain its operational tempo, it dramatically accelerated its advance. Conversely, German panzer divisions found themselves utterly incapable of replenishing their losses. A Panther tank, destroyed in the hedgerows of Normandy, was, for all practical purposes, permanently removed from the battlefield. While German factories might eventually construct a replacement, the monumental task of transporting it to the embattled front in France, through skies dominated by overwhelming Allied air superiority, rendered such an effort virtually impossible. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The logistical dimension represented the true chokehold applied by American industrial might upon the German war machine. Consider the prodigious fuel consumption of a Sherman tank, which devoured approximately 150 gallons of fuel for every 100 miles traveled. When multiplied across thousands of operational tanks, this figure underscores the monumental output of the U.S. petroleum industry, which in 1944 alone produced an astonishing 5 billion barrels of oil, a quantity exceeding the combined production of all other combatant nations. Germany, by stark contrast, managed to produce only about 40 million barrels in the same year, with the vast majority of this supply being synthetic fuel derived from coal. When Allied bombers systematically targeted and devastated German synthetic fuel plants in mid-1944, the consequences were immediate and dire. Panzer divisions found themselves literally immobilized, running out of the very essence of mobility. The desperate Ardennes offensive in December 1944, famously known as the Battle of the Bulge, was fundamentally predicated on the German objective of seizing American fuel depots, precisely because their own supplies were woefully insufficient to sustain such an ambitious and lengthy operation. Beyond combat losses, the critical scarcity of spare parts proved equally destructive to German operational readiness. If a Sherman tank suffered a broken track or a malfunctioning transmission, replacement components would typically arrive within a matter of days from vast supply depots, brimming with thousands of necessary parts. German tanks, however, were plagued by constant mechanical failures. The final drive of the Panther tank, for instance, was notoriously fragile, often failing after an average of just 150 kilometers in early production models. Yet replacement final drives simply did not exist in adequate quantities to meet demand. German units frequently reported that 30–50% of their tanks were non-operational due to mechanical breakdowns, rather than direct combat damage. This dire situation forced them into the desperate and unsustainable practice of cannibalizing broken tanks for parts to keep others running, a self-defeating spiral that inevitably guaranteed a continuous decline in overall operational strength. The disparity in crew training pipelines further illuminated the profound advantage of American industrial superiority. U.S. tank training schools, prominently located at Fort Knox and Fort Benning, successfully graduated thousands of highly skilled crews annually, each having received a rigorous 12 to 16 weeks of comprehensive instruction. Consequently, when a Sherman crew was tragically lost in battle, a robust pool of 5 fully trained replacements was readily available stateside. Germany's training infrastructure, however, had largely collapsed by 1944. Replacement crews received mere weeks rather than months of instruction, and frequently encountered the specific tank model they were assigned to operate for the very first time upon their arrival at the front lines. These inexperienced crews inadvertently exacerbated the inherent mechanical unreliability of German tanks. Lacking the necessary expertise to operate complex systems correctly, they inadvertently contributed to an increased incidence of breakdowns and, tragically, higher combat losses. The strategic bombing campaign, a monumental undertaking made possible by the immense capacity of American industry, effectively closed the loop on Germany's industrial demise. The very same factories that churned out Shermans also produced B-17s and B-24s by the thousands. These formidable bomber fleets systematically dismantled German industrial capacity from 1943 onward. Critical targets included the ball-bearing plants at Schweinfurt, the vital synthetic oil facilities nestled in the Ruhr region, and the locomotive works essential for moving supplies. All were deliberately targeted because American intelligence keenly understood that Germany's strained war economy simply could not absorb such widespread disruption in the same resilient manner as America's could. When Allied bombs obliterated a German tank factory, it remained destroyed. America, in stark contrast, possessed the unparalleled ability to lose an entire factory and simply construct another, or shift production elsewhere. The final tally of industrial output paints an exceptionally stark picture. Germany produced approximately 25,000 Panthers and Tigers combined, representing their most advanced and formidable tanks. In the same period, America manufactured an astounding 49,000 Shermans. Yet, American production extended far beyond just the Sherman. It also included 24,000 light tanks, 2,400 heavy tanks, 89,000 aircraft, and 5,000 crucial cargo ships, within the identical time frame. This industrial output was not merely superior, it was existentially overwhelming, fundamentally determining the course of the conflict. Germany attempted to wage World War II with the industrial capacity of what amounted to a regional power, while America engaged with the colossal productive might of an entire continent. The ultimate outcome, therefore, was never genuinely in doubt once those prolific car plants began their transformative shift to building tanks.